Okay. Okay, so consider a thin, infinitely wide conducting sheet, so it's a conductor, okay, with a thickness delta and area A. So it has a thickness and it has an area such that A is much greater than delta squared. And now, of course, the title here, you say Gauss's law for electricity. This means that you need to use Gauss's law for electricity. That's the bottom line of it, all right? And this sentence here, I'm stating that the area is much greater than delta, so I'm gonna neglect the effect of the boundaries, okay? We remove a certain number of n of free electrons to charge it and neglect all effects occurring at the edge of the sheet. Exactly. So the question is, the first is determine the charge density of the conducting sheet. So here there are two issues. One is that you need to realize that for a conducting sheet, the charge they lie only on the surface of the sheet. Okay? Consequently, here I say the charge density. I don't say if it is linear charge density, volumetric charge density, or surface charge density. So this means that you guys here should guess that it is the surface charge density since the charges lie only on the surface. This is one. So basically, then you write sigma is equal to Q divided by A, where now what is Q? Q is equal to N multiplied by small q, by the elementary charge. And what is A? A here, since it has a thickness, so basically A is equal to 2 A's because the charges now are on the top and on the bottom of the surface. Okay? So in this case here, let me see if I can annotate here. I can annotate, yes. All right. So here, what the answer should be, since it is a conductor, the charges lie on the surface and sigma equal to Q divided by, let's say, Q divided by 2A. You can write like this, or is equal to small q n divided by 2A. So here, there is this term here, the conductor, and then the surface, and the surface sigma is the, and what we say is that, and the surface charge density sigma is equal to nq divided by A. Okay. Now, what is the electric field inside the sheet? Well, once again, since it's a conductor in electricity equilibrium, okay. Since the conductor is in electrostatic equilibrium, then E inside equal to 0. That's it. Okay. We don't need. That's it. That's the answer. Okay. All right. Let's continue. It seems like it's okay. We can do it. So we move on. Ah, look what happens. Oh, that's pretty bad, guys. Okay, are you guys taking notes? Because I will have to solve each problem at a time.
Yes.
Okay.
You can
okay. So I'm going to lead. All right. Okay. Let's continue with this one. Determine the electric field outside the sheet at distance p, at distance xp from its surface. Okay. So here we're going to say that now we're going to use Gauss's law. Okay. integral of E scalar dA equal charge inside divided by epsilon 0. Okay, and this integral is what you call it is over the Gaussian surface. Okay, so then my second point is to determine the Gaussian surface. So the Gaussian surface GS is, I'm going to say it's a cylinder. It's a cylinder with length xp plus x, okay, and with yes, and a diameter r, arbitrary diameter r. So basically now, if I'm going to draw something, let me see, draw. That would be my Gaussian surface. Voilà. It passes by P where I want to calculate it. Now you can tell me, okay, I put it here inside, right? So I put it here inside, and this distance is completely arbitrary, all right? So this distance from here to here, that's my x, all right? I'm going to say plus x, if I'm going to say it's x in okay, well, it seems like I cannot go back to. Okay, so this is my x, so I put this is my Gauss surface, it is well defined. Okay, it is well defined, and now this will end in 10 minutes, okay? And now I can continue. So the first part, what we said is that second, what you need to do as a second step is to determine the integration. So determine the integration. Okay, and now what we say, the int, and this is integral, okay, backslash int is integral, over my Gaussian surface is equal to int over the top, so the top of the cylinder, plus int bottom, plus int side. Okay, now what does int at the bottom is equal to? Is equal to the electric field multiplied by the area A. Okay, here I have theta is equal to 0. Okay, give me a second. I'm sorry, but I'm used to writing in LaTeX. I think you guys should learn how to write in LaTeX. So int of the top is equal, has theta is equal to 0, and I will assume r, the radius, to be small, such that E is uniform inside. Okay, and consequently, the integration int top is equal E multiplied by A of the Gaussian surface. Yani it's equal to E multiplied by 4 pi r squared. Okay, so now we have that's the left hand side. Now we want to know the I need to go the bottom one. And bottom is equal to dash, you know, is equal to 0 because E is equal to 0. Okay, let me double check what I have here. R, yes, it's the radius of the cylinder, yes? Yes, so R is the radius of the cylinder, okay? So this is here, that's cylinder, this is the side. That's what you see here. That's the side of the side of the cylinder. So here is going to be the cylinder. Okay. Now I have int on the side, so the side of the cylinder. Int side is also equal to 0 because theta is equal to 90 degrees. Okay, wherever you are on my cylinder, if this is your paper and that's your cylinder, okay, wherever you are, then the electric field will be perpendicular to the okay. So this gives us that the integral over my Gaussian surface is equal to E multiplied by A of my Gaussian surface. All right. Now we turn into the third part, which is determining Q inside. All right. Q inside, Qn is only at the surface. And if I have determined sigma above, right? I know sigma determined in question 1. Okay, then Qn is equal to sigma okay, multiplied by the area of the Gaussian surface. So AGS, which is sigma multiplied by 4 pi r squared. Okay? Answer the question. And now we have E. Now we have E multiplied by A Gaussian surface equal Q inside, which is sigma, divided by, multiplied by A Gaussian surface divided by epsilon 0. And this will lead to E equal sigma divided by epsilon 0. Of course, I think that you guys all agree, and you have probably guessed that this was done in class, right? Of course, I don't know if we did it, but I think we did it, yes. Okay, so this was done in the class, so that's what. So what I'm trying to say is that, you know, you can see that the problems that are given are actually something which quite close to what we did in class. Okay, any questions on C? Okay, I'm going to continue then. Okay, come on. Okay, I'm going to erase. I'm sorry. Can I erase? Any problem with erasing? I hope that you guys are following it up. Otherwise, it's not a problem. So basically now I need to get the potential difference between 2 points A inside and B. Okay. Now what I need to do, I need to use, very important, we need to use the definitions that were given. What's the potential difference? Well, the delta V between 2 points A and B is equal to minus integral of A to B, okay, point A to point, excuse me, to point P, to point P, so from P, so delta V A P. So the question, what's the potential difference between an arbitrary point, two arbitrary point, one inside and the other one is outside, okay? So this is integration of E scalar ds, right? So that's your first step, is that state the main equation that you guys need to use, all right? Then what I can say is that actually let A prime be a point on the surface. Why? I'm going to say that because I'm going to say integration between A to P is equal to integration between A to A prime plus integration between A prime and P. Okay? That was the trick in this question. Okay? Now, so what is the integration between, so this is equal, what's the integration between A and A prime? This is equal to 0, right? Because E is equal to 0, right? EDS. So since it's equal to 0, then it's equal to 0. Plus integration between A prime and P of E scalar ds. E is in this direction and ds is in this direction. So E ds. Okay? E ds, E is uniform, so it gets out. So this is equal to E integration between A prime to P of ds. Okay? So the integration of ds, that's the length s, which is basically xp. So that's equal to E multiplied by xp. Sorry, there's a minus sign that I forget here. But if the important is to determine the potential difference between two arbitrary points. So the two arbitrary points, delta VAP is equal to minus E multiplied by XP. Okay? Okay. Any questions?